Bob. Today we're looking at mechanics, resisted motion under gravity, the rising and falling of the minion, and basically the velocity squared is actually what the resistance is proportional to. This case was last video, it was actually just proportional to the velocity. We've actually put the constant in as 1/50th or 0.02, and as I said last time, no minions were harmed in the making of these videos. So obviously we look at the case where he rises up to a maximum height and look at the time, and then when he comes back down to the ground, he falls basically from that particular height where he went up to, and he comes back down to ground, and we look at the velocity he reaches at the ground and also how long he takes. Okay, so let's have a look. I'll try and get this pen working again. Okay, so basically we set the equation up again as usual. The equation is basically set up from the forces, the forces which are basically the net resultant force, which is in the upward direction, which is positive, and the resistance force and gravity are the other two forces, which are obviously acting in the opposite direction. That's why they're negative. And we're taking gravity is about 10 meters per second per second. Okay, just a bit of an approximation, just to make life a little bit easier. The minion again is given an initial velocity of 60 meters a second. Have a look over here. These are the initial conditions, and at time is 0, he was initially projected up at 60 meters a second from the ground, 0 position, x is 0. And we now look at well, we want x, so we want the height x, and so we look at an expression for acceleration with an x in it, which is v dv dx. So we replace acceleration with v dv dx equals minus 10 minus v squared on 50, and we now proceed to manipulate this. Basically, we've got to separate the variables, so we just do a bit of fraction work. We then divide by v. Then we take the reciprocals of both sides, and then we basically try and separate the variables so we can start to integrate. Okay. Alright, so let's have a look at what happens when we start to integrate. Well, we are integrating from 0 to height, well, h, I should say, the height, which we don't know really. It's this is something we're basically after. And we, yeah, there's a few things happening at the moment in the background there. But 0 to h and the 60 to 0, we know that its velocity at the top or with maximum height will in fact be 0. So we know we can integrate from 60 to 0. Now you notice I've split the 50 up into 2 lots of 25, so that makes the integral a little bit easier. Okay, so we now have h is equal to minus 25 L in 500 plus v squared, so just a log integral, and we need to evaluate this. Okay, so you can just see here this turns out to be about what, 52.60 meters high, and you'll notice that that was actually much lower than if it was going up well, with the velocity just, or the resistance was just proportional to normal velocity. In the last video we're up to about 168 meters. Okay, all right, so let's have a look at the time taken to reach this particular height. Okay, so here we go. Okay, so again we start off with the same equations of motion, and just x dot product was minus 10 minus v squared on 50. Now you might see that we are obviously after the time, so we have to use an expression for the time, or dv dt, as x double dot. So we need to get the time from this integral. We do a bit of fraction work. You can see here we take the reciprocals of both sides, and then we separate the variables. And then we obviously we separate these to start to integrate. Now you can see this going up. Okay, so let's actually have a quick look over here. Let's try and move the. Okay, here we go. Now we're going to integrate. Okay, from 0 to time t. We don't know what the time is. Okay, but we do know that it's going to go up to the maximum height, and its velocity will in fact be 0 at the maximum height. And it was initially at 60. Okay. Now you'll see that this is actually a standard integral. It's an inverse tan integral. I'll just put the standard integral in here, and you can see here, what is it? T is about minus 50 on the square root of 500 inverse tan v on the square root of 500 from 60 to 0. Okay, we need to put this in. You can see I took the negative sign in there, and we get about 2.71 seconds to reach that maximum height of about 52.6 meters. Okay, all right, let's look at the down case now. Okay, falling, here we go. Now, oops, I think I'll just jump forward a couple. Yes, okay, here we go. Now, we want to first of all work out basically the velocity on the, when the minion reaches the ground. Now, the idea obviously is we have to sort of change the equations of motion here. Obviously, because the what's happening is, we're falling down, so the down's a positive direction, and the basically we now, if you have a look over, we've got let's actually close that down for a minute. Let's have a look over here. Here's a minion. Okay, now it's falling down, so obviously 10 is in the positive direction. The v squared on the 50 is in the negative direction. This is why the net force is now acting down in the same direction as gravity, which is 10 meters a second. Okay. Now we'll try and get this pen working again. So, okay. Sometimes I'm a bit rough with this. It doesn't like it. I didn't like it that time. Okay. So let's see if we can get it to work out here. I didn't like it that time either. Okay, let's try one more time over here. Okay. Yes, okay. That seems to be a bit fiddly at the moment. Okay, so x double dot equals 10 minus v squared on 50, and we're first of all we're after the velocity when it reaches the ground. So we need okay, v dv dx. Okay, why do we need v dv dx? Well, we know how high it is, so we know the x, but we don't know the velocity. So we are going to basically find an expression for the velocity with the height, or with x. Okay, so what do? Well, we divide by v, we take the reciprocals, we separate the variables, and then we start to integrate. Now, what are we integrating from? Well, basically, because down is positive now, we are going from 0, which we're going to take as the top, back down to the ground, which is, you might remember, was 52.6 meters away. And we have to try and, you can see here it's going to be a log integral. I split it up with two negatives there. 2 times 25. Okay. Okay. So we now have to. We know that the height is 52.6, and we get an expression which has got the height in it and the velocity, and we need to basically solve that equation for the velocity, which we can do in this case. It's not a transcendental function. It's a transcendental equation. We can actually it is just a log equation, so we can just solve that. Okay. Although logs are transcendental functions themselves, but it's just a log equals a particular constant, so it's solvable, and we have to raise it into the power e. I see here a few things I've done, and we've actually found the reciprocal of both sides and used the negative power for the exponential, and then we have to basically solve for the velocity, and the velocity turns out to be about 20.95 meters a second when the minion reaches the ground. Okay. Now, how long does it take to get to the ground? Well, let's have a quick look. Okay, so again, now the equation you can see here again is obviously 10 minus v squared on 50 as before. We now need to find an expression for the time, so we need the acceleration to be expressed in terms of the time. So we need x double dot equals to v dt, which is 10 minus v squared on 50. We just do some fraction work, we take the reciprocals, and then we separate the variables. Okay. Now, if you go over here, you can see that I've going to use a special integral here in a second, but you can do this by integration by parts, but sorry, partial, I should say partial fractions. So we're going to integrate from 0 to t to get the time, basically, and we've got okay, the velocity is going from 0 to 20.95 to when it reaches the ground, obviously. And we have to try and work out basically the time for that particular velocity. So, okay, we use you can see here, this is the standard integral I've got here, the d squared on a squared minus x squared is 1 and 2a ln a plus x all over a minus x. Okay, so it's nice and handy. I mean, if you have to derive that, it can get a little bit tedious with partial fractions. Okay, so we basically just sub it into this standard integral, and we end up getting that the time's about, you can see here, 3.83 seconds. So you can see it's about 1.12 seconds longer. Okay, this is actually much longer on the return trip than the earlier video. You see it was only about 0.25 seconds longer, the up and down trip, and this is actually quite a bit longer. Okay, well, that's all for today, and thank you for watching, and bye for now.